Welcome to Innovation Pulse, your quick, no-nonsense update on the latest in AI. First, we will cover the latest news. OpenAI is enhancing ChatGPT's memory for pro users. YouTube adds AI music tools. Spammers misuse AI tech. And Gemini 2.5 Pro expands research capabilities. After this, we'll dive deep into Google's strategic move with their new Ironwood TPU, transforming AI inference and its impact on the market. Stay tuned. OpenAI is enhancing ChatGPT with a memory feature that allows it to recall past conversations, even if users haven't manually saved them. CEO Sam Altman announced that this update supports the goal of creating AI that grows alongside users. This new capability builds on a previous memory feature that retained limited data for future interactions. The update distinguishes between saved memories and reference chat history, using insights from past interactions to improve future responses. However, it's not available in the European Union, United Kingdom, Switzerland, Norway, Iceland, and Liechtenstein due to strict AI regulations. The rollout is initially for users on ChatGPT's $200 Pro subscription, with plans to extend to $20 plus subscribers and other tiers soon. Users can opt out of this feature through personalization settings, ensuring their privacy preferences are respected. Next, we'll discuss the impact of BrowseComp. OpenAI has introduced BrowseComp, a new open-source benchmark for evaluating AI agents' web browsing capabilities. BrowseComp contains 1,266 challenging questions designed to test how well AI can locate and analyze complex information on the web, simulating real-world scenarios like academic research or market analysis. This benchmark emphasizes finding hidden treasures in information-rich environments, rather than answering common questions. By open-sourcing BrowseComp, OpenAI aims to foster global collaboration and innovation, offering developers a tool to optimize AI performance in real-world web settings. Initial evaluations show models trained for deep web research, like Deep Research, excel in complex tasks, highlighting BrowseComp's effectiveness in distinguishing model capabilities. BrowseComp's release paves the way for smarter AI applications, crucial for businesses, academia, and individual users. It also prompts discussions on AI ethics, such as data privacy and algorithmic bias, encouraging a safer AI ecosystem. YouTube has introduced an AI-powered music feature for creators, allowing them to generate royalty-free instrumental tracks directly in Creator Music. This tool helps streamline the process of finding music by enabling creators to describe the vibe they want, including instruments and mood. The AI then creates a custom track, free from licensing worries. Initially available to US-based creators in the YouTube Partner Program, this feature aims to reduce time spent searching for music, allowing more focus on content creation. While it doesn't replace human composers, it simplifies soundtrack creation at scale. This development showcases YouTube's commitment to enhancing creative control, setting a foundation for creators to integrate original music into their brand effortlessly. The move reflects a strategic step beyond simply competing with platforms like TikTok or Reels. Spammers exploited OpenAI's capabilities to send unique messages to over 80,000 websites, evading spam filters. This was detailed by Sentinel Labs researchers. They highlighted the dual nature of large language models, which can be used for both helpful and harmful purposes. The spammers, using a framework called AkiraBot, automated sending messages to promote dubious SEO services. AkiraBot employed Python scripts to vary domain names and used OpenAI's Chat API, GPT-4o Mini, to tailor messages for each site. This customization helped bypass filters that block identical content. Messages were sent via contact forms and live chats on targeted websites. Researchers emphasize the challenges AI poses in defending against spam. OpenAI, recognizing the misuse of its service, revoked the spammer's account and thanked the researchers for their findings. Join us as we step into the future of advanced AI research. Gemini 2.5 Pro Experimental now includes deep research. Available to Gemini Advanced subscribers, this powerful AI model, recognized for its capabilities, enhances the research process. In testing, reports generated by Gemini Deep Research were favored over other providers by more than a 2-to-1 margin. Users note significant improvements in analytical reasoning and information synthesis, resulting in more insightful reports. This feature is accessible on the web, Android, and iOS, allowing users to generate comprehensive reports on various topics, saving hours. Additionally, the Audio Overviews feature can transform reports into podcast-style conversations for easy listening on the go. Users can explore these features by selecting Gemini 2.5 Pro, Experimental, and choosing Deep Research in the prompt bar. Elon Musk's xAI, despite facing a lawsuit from OpenAI, is pushing forward with its Grok 3 AI model, now available via API. Grok 3, launched months ago, competes with models like GPT-4o and Google's Gemini, offering image analysis and question responses. xAI provides Grok 3 and its mini version, both featuring reasoning capabilities at varying costs. The pricing matches Anthropic's Claude 3.7 Sonnet, but is higher than Google's Gemini 2.5 Pro. Grok 3's context window is smaller than advertised, handling up to 131,072 tokens instead of the claimed 1 million. Musk initially described Grok as edgy and controversial, willing to tackle topics other AIs avoid. However, earlier versions leaned politically left, which Musk attributes to its training data. He aims to make Grok politically neutral, though the effectiveness of this shift remains uncertain. And now, pivot our discussion towards the main AI topic. Today, we're going to explore Google's latest advancement in AI hardware, the Ironwood Tensor Processing Unit. During Google Cloud Next 25, the tech giant unveiled this new custom chip designed specifically for AI inference, marking a significant shift in their hardware strategy. We're joined by tech analyst Yakov Lasker to discuss what this means for the industry, Google's competition with NVIDIA, and the economics of AI computing. Welcome to the show, Yakov.
Thanks for having me, Robbie. I've been following Google's TPU journey for years, and this announcement represents a fascinating pivot in their strategy. I'm excited to dive into the details with you today. Feel free to ask your first question.
Let's start with the basics. For our listeners who might not be familiar, what exactly is a TPU, and how does Google's development of these chips fit into the broader AI hardware landscape?
A tensor processing unit, or TPU, is a specialized chip designed by Google specifically to accelerate AI workloads. Unlike general-purpose CPUs or even GPUs, TPUs are application-specific integrated circuits, ASICs, built from the ground up for tensor operations, the mathematical calculations that power modern machine learning models. Google's been developing these chips in-house for over a decade now, through 6 previous generations before Ironwood. While companies like NVIDIA focus on creating versatile chips sold to everyone, Google's TPU strategy was initially about creating custom silicon for their own AI research needs. This allowed them to optimize specific workloads that they knew they'd be running repeatedly.
That's helpful context. What makes this new Ironwood TPU announcement particularly significant compared to previous versions?
What's truly groundbreaking about Ironwood is that it's the first TPU Google has positioned primarily for inference rather than training. Previous generations were either focused on training, the resource-intensive process of developing neural networks, or pitched as dual-purpose chips that could handle both training and inference. Ironwood marks a strategic pivot to focus on inference, which is the process of using already trained AI models to make predictions for real-world requests from users. This shift reflects the maturing AI industry, where we're moving from primarily research and development to actual widespread deployment of AI systems, serving billions of users daily.
You mentioned the distinction between inference and training. Could you elaborate on that difference and why it matters for chip design?
Absolutely. Training is the process where an AI model learns patterns from data. Think of it as the education phase. This requires massive computational power, but happens relatively infrequently. For a company like Google, they might train a major new model version just once or twice a year. Inference, on the other hand, is when the trained model makes predictions or generates content for real users, like when Google Assistant answers your question or Gmail suggests replies. Inference happens billions of times daily across Google's products. The computational requirements differ significantly. Training needs to process huge datasets repeatedly, while inference must deliver low-latency responses to millions of concurrent users.
That makes sense. So why is Google suddenly shifting its TPU focus toward inference now, after years of emphasizing training capabilities?
The timing aligns with an economic inflection point in AI. First, we're seeing companies move from experimental AI projects to deploying production models that serve real customers, shifting demand from training to inference. Second, the emergence of reasoning AI models, like Google's Gemini, has dramatically increased inference costs. These reasoning models don't just generate simple responses. They perform multi-step thinking processes that can require 100x more computation than earlier models. As Google noted when describing Ironwood, reasoning and multi-step inference is shifting the incremental demand for compute, and therefore cost, from training to inference time. With inference now consuming more resources than ever, optimizing those costs becomes critical to Google's bottom line.
Speaking of economics, can you help us understand the market dynamics between training chips and inference chips in the industry?
Training chips occupy what we call a lower volume market. Only research labs and a handful of tech giants have the resources to train massive foundation models, and they only do so periodically. These customers might buy thousands of chips for their training clusters. Inference, however, is a high-volume market. Every company deploying AI, from startups to enterprises to cloud providers, needs inference chips to serve their customers daily. This could mean millions of chips distributed across data centers worldwide. From a chip manufacturer's perspective, inference represents a much larger revenue opportunity, which explains why Google might be repositioning its TPU program to capture this growing market.
Let's talk about the competition. How do Google's TPUs compare to NVIDIA's GPUs, which seem to dominate the AI chip market currently?
NVIDIA GPUs and Google TPUs represent fundamentally different approaches to AI acceleration. NVIDIA's GPUs were originally designed for computer graphics, but have evolved to be remarkably effective for AI through their parallel processing capabilities and robust software ecosystem, CUDA being the crown jewel that developers love. TPUs, being purpose-built for AI, can achieve higher performance and energy efficiency for specific workloads. They excel at the matrix multiplication operations central to neural networks. However, Google's TPUs have historically been available only within Google's ecosystem, while NVIDIA sells to everyone. TPUs also lack the software flexibility of GPUs. They're optimized for Google's TensorFlow and JAX frameworks specifically.
We've seen reports about the enormous costs of building and running large AI models. How might Ironwood impact Google's economics in this AI arms race?
The economics here are fascinating. Wall Street analysts estimate that if Google were selling TPUs as hardware to NVIDIA customers, they could have generated up to $24 billion in revenue last year, indicating the substantial value of this technology. For Google itself, greater adoption of in-house TPUs could significantly reduce their AI infrastructure costs compared to purchasing chips from vendors like NVIDIA, whose GPUs command premium prices due to overwhelming demand. With projects like DeepSeek and Stargate pushing AI infrastructure costs into the hundreds of billions, even modest efficiency improvements translate to enormous savings. This cost advantage could help Google remain competitive, with other tech giants investing heavily in AI.
You mentioned that Google has been developing TPUs for over a decade. How has their chip strategy evolved over the generations?
Google's TPU journey reflects their evolving AI ambitions. The first generation TPU, revealed in 2016, was focused solely on inference for existing models. With the second generation in 2017, Google began talking about combined abilities for both training and inference, reflecting their expanding research goals. As Google's AI models grew more complex, so did their chips. The fourth and fifth generations brought massive performance improvements, while the sixth generation Trillium TPU, which became generally available just last December, was positioned as a versatile chip for both training and serving predictions. Ironwood represents yet another pivot, acknowledging that inference is now where the largest computational demands and costs are emerging.
Google Cloud currently relies heavily on chips from Intel, AMD, and NVIDIA. Does Ironwood signal a change in that relationship?
This is perhaps the most significant strategic implication. According to research from KeyBank Capital Markets, Intel, AMD, and NVIDIA chips currently make up about 99% of processors used in Google Cloud instances, with TPUs accounting for less than 1%. Ironwood likely signals Google's intent to reduce this dependency on external chip suppliers. While Google had previously described TPUs as necessary for cutting-edge research, but not alternatives to commercial chips, this explicit push into the inference market suggests they're now willing to compete more directly with traditional suppliers. This could dramatically alter the power dynamics between Google and chip vendors like NVIDIA, whose AI chips command premium prices due to unprecedented demand.
We've been hearing a lot about new reasoning AI models. Could you explain what these are and why they particularly impact inference costs?
Reasoning AI models represent the next evolution in large language models. Traditional LLMs, like earlier versions of ChatGPT or Bard, generate responses based on pattern recognition and prediction. Reasoning models like Google's Gemini or Anthropic's Claude add an extra layer. They simulate a thought process, breaking problems into steps and thinking things through before responding. This approach dramatically improves capabilities for complex tasks, but comes at a computational cost. A reasoning model might generate 10 to 50 times more internal statements than what the user sees in the final output. This test time scaling, as Google calls it, shifts the computational burden heavily toward inference time. Optimizing for these workflows requires specialized hardware designs, which is precisely what Ironwood aims to address.
Let's talk about the manufacturing side. Google doesn't fabricate these chips themselves, right? How does production work?
That's correct. While Google designs their TPUs in-house, they partner with external manufacturers for production. For several generations, they've worked with chipmaker BrowseComp to help take each new TPU design into commercial production. This arrangement allows Google to focus on their core competency, chip architecture optimized for their AI workloads, while leveraging BrowseComp's manufacturing expertise. It's worth noting that this differs from NVIDIA's approach, which works with foundries like TSMC but handles more of the chip design and commercialization process themselves. Google's approach might offer flexibility, but potentially at the cost of some margin that goes to their manufacturing partners.
How might Ironwood impact developers and businesses using Google Cloud?
For Google Cloud customers, Ironwood could translate to better performance and potentially lower costs when running inference workloads. Developers might see new service tiers or instance types optimized specifically for serving AI predictions at scale. Businesses deploying reasoning-heavy AI applications could benefit most significantly, as these workloads align precisely with Ironwood's design goals. I expect Google will position these chips as differentiators against competing cloud providers, particularly for customers who need cost-effective scaling for advanced AI capabilities. The key question is whether Google will pass those cost savings on to customers or capture them as improved margins.
The article mentioned DeepSeek AI. Can you elaborate on how developments like that have influenced Google's chip strategy?
DeepSeek AI represents a fascinating case study in AI economics. They've created models that can outperform much more expensive options, but at a fraction of the cost. Wall Street analysts have been particularly focused on this development because it demonstrates that spending efficiency, not just raw investment, matters tremendously in AI. This focus on cost efficiency puts pressure on Google and other tech giants to optimize their AI infrastructure spending. When analysts see companies achieving comparable results with smaller budgets, they naturally question whether the massive capital expenditures by bigger players are justified. Ironwood appears to be part of Google's response, demonstrating that they're innovating to improve the economics of AI at scale, rather than simply throwing more resources at the problem.
Let's talk energy efficiency. How does this factor into Google's chip strategy with Ironwood?
Energy efficiency is absolutely critical in modern data centers, both for operational costs and environmental impact. TPUs have traditionally offered better performance per watt for specific AI workloads compared to general-purpose processors or GPUs. With Ironwood focusing on inference, which runs 24/7 across global data centers, the energy savings could be substantial. Google's data centers already consume enormous amounts of electricity, and AI workloads are increasingly driving that consumption. By optimizing specifically for inference efficiency, Google can better manage their carbon footprint while keeping operating costs in check. This is especially important as inference workloads continue to grow with the proliferation of AI-powered services.
How might Ironwood impact Google's competitive position against other cloud providers like Microsoft and Amazon, who are heavily investing in AI?
This represents a potential competitive advantage for Google in the cloud wars. Both Microsoft and Amazon rely heavily on NVIDIA GPUs for their AI offerings, which means they're subject to supply constraints and premium pricing that have characterized the GPU market recently. If Google can scale deployment of Ironwood TPUs effectively, they could offer inference capabilities at price points or performance levels that competitors can't match using off-the-shelf GPUs. This would be particularly valuable for attracting enterprise customers who are looking to deploy AI at scale, but are concerned about costs. However, the advantage depends on whether Google can manufacture TPUs at sufficient volume and whether their software ecosystem can match the development flexibility that NVIDIA's CUDA provides.
Looking ahead, what does this shift toward inference-focused chips tell us about the future direction of AI hardware?
I believe we're witnessing the beginning of greater specialization in AI silicon. The first wave of AI acceleration was about getting models to work at all. NVIDIA's GPUs were remarkably well suited for this due to their parallel processing capabilities. The second wave was about massive scaling for training ever larger models, leading to specialized training clusters. This third wave, exemplified by Ironwood, focuses on making AI economically viable at scale. We'll likely see increasing divergence between training and inference hardware, with each optimized for their specific workloads. I also expect vertically integrated companies like Google to gain advantages by tailoring hardware precisely to their software needs, creating performance and efficiency gains that general-purpose solutions can't match.
Finally, do you think we'll see Google offer these TPUs to external customers similar to how NVIDIA sells their GPUs?
While Google hasn't explicitly stated plans to sell TPUs as standalone hardware, the economics suggest they might consider it. If Wall Street analysts are correct that Google could generate $24 billion selling TPUs to the market, that's a compelling business opportunity. However, I think it's more likely that Google will keep TPUs primarily within their ecosystem, offering them through Google Cloud Services rather than as purchasable hardware. This allows them to maintain control over the full stack and capture recurring revenue through cloud services rather than one-time hardware sales. It also aligns with their broader strategy of using proprietary technology to differentiate their cloud offerings in an increasingly competitive market.
Yakov, thank you for sharing your insights on Google's Ironwood TPU and helping us understand the broader implications for the AI hardware landscape. This has been an enlightening conversation about the economics and technology driving the next generation of AI computing.
It's been my pleasure, Robbie. The AI hardware space is evolving rapidly, and developments like Ironwood reveal how the industry is maturing from research projects to production-scale deployment. I look forward to seeing how Google's inference-focused strategy unfolds, and how competitors respond in this increasingly crucial battleground for tech supremacy.
That's a wrap for today's podcast. OpenAI is enhancing ChatGPT with memory features and tackling spam misuse, while Google pivots to the Ironwood TPU for AI inference efficiency, potentially challenging NVIDIA's market dominance. Don't forget to like, subscribe, and share this episode with your friends and colleagues so they can also stay updated on the latest news and gain powerful insights. Stay tuned for more updates.